The topic of this lesson is inductance in DC circuits, the comparison of resistance and inductance. Apart from resistance, a circuit may possess two other properties, inductance and capacitance. Inductance may be defined as that property, electrical in nature, that resists a change in current and thus limits the rate of change of current. It is analogous to mass in mechanics. Just as the velocity of a mass cannot change instantaneously on application of a force, and inductance cannot have current flowing through it changed instantaneously. The property of inductance is more pronounced in a coil than a straight piece of wire, and inductance may also be regarded as having energy stored in a magnetic field. This energy is invariably drawn from a source. In comparison, a resistance takes energy from a source and dissipates it in the form of heat. The circuit symbol for an inductor is shown, and its symbol is the letter L. The unit is the Henry. A typical coil would possess both inductance and resistance. Let's look at an example. To understand the difference between a resistor and an inductor, let us imagine a circuit having a resistor and an inductor connected in parallel across a DC source. We will assume initially that the inductor is made up of a coil of negligible resistance and possesses inductance only. When the switch is closed, the current in the resistor R instantaneously changes from 0 to a constant value. I sub R is equal to E divided by R, or 20 divided by 6, which equals 3.33 amps. And the voltage drop across the resistor is equal to V sub R, which is equal to minus I sub R times R. This voltage opposes or balances the source voltage using KVL, Kirchhoff's voltage laws. E plus V sub R equals 0. Therefore, E is equal to minus V sub R, or E is equal to I sub R times R. In the inductor, however, when the switch is closed, the current begins to increase in the coil. A magnetic flux is created which, as it expands outward, interacts with the turns of the coil itself. According to Faraday's law, an EMF will be induced in the coil, V sub L, and this, like V sub R, will exactly oppose and counterbalance the source voltage E. That the polarity of the induced EMF is such as to oppose the change in current producing it is given by Lenz's law. V sub L is dependent on the inductance L and is determined by the number of turns in the coil, the type of core, the cross-sectional area, and the length. The opposition EMF must be proportional to the rate of change of current. V sub L is equal to minus L times delta I sub L divided by delta T, where V sub L is equal to the counter EMF. The negative voltage sign indicates that its polarity is opposite to that of the source EMF. L is equal to the coil's inductance in henries, and delta I sub L divided by delta T is equal to the rate of change of current. As an illustration, if, after the switch is closed, the value of I sub L after 4 seconds and 6 seconds are 10 amps and 16 amps, then delta I sub L is equal to 16 amps minus 10 amps, or 6 amps, and delta T is equal to 6 seconds minus 4 seconds, or 2 seconds. Thus, delta I sub L divided by delta T is equal to 6 amps divided by 2 seconds, or 3 amps per second. This is the initial increase in current. Using Kirchhoff's voltage law in the loop containing the inductor, E is equal to V sub L, which is equal to 0. Therefore, E is equal to minus V sub L, or L times delta I sub L divided by delta T. Thus, L is equal to E divided by delta I sub L divided by delta T in henries. This is also known as self-inductance, or L is equal to 20 volts divided by 3 amps per second, which is equal to 6.67 henries. In our previous example, we neglected the resistance. In reality, the steady-state current through the inductor still obeys Ohm's law, or I is equal to R divided by E, or 20 volts divided by 3 ohms, and is equal to 6.67 amps. The total or final current is I is equal to 3 plus 6.67, which is equal to 9.67 amps.